Okay, it's my pleasure to introduce Javier Fochesatto.
Fochesatto, yeah.
Okay, sorry for that slight German accent and butchering it. Javier from the Geophysical Institute at the University of Fairbanks, Alaska, where he is an associate professor in atmospheric sciences. His main research focuses atmospheric boundary layer and micrometeorology right there, studying these processes using LiDAR, Doppler sonar, GPS soundings, scintillometer, 80 flux towers. So I expect to see a lot of observations. Javier has worked internationally a fair bit, some cooperations with Jamstack in Japan, Copri in Korea, and then a larger collaboration in Europe with France, Belgium, Norway, Russia, Chile, Uruguay, so they're not in Europe, South America, and the US.
Little Europe.
Javier got his degree at the Laboratoire de Météorologie Dynamique of CNRS in France, in Palaiseau. And his work history is actually quite varied. He has a lot of experience in lasers, built lasers at the Universidad de Buenos Aires in Argentina, and at the Centro de Investigaciones en Láseres y Aplicaciones. And then in 2003, I believe, he moved to Waterloo, Canada, where he was at the Department of Chemistry. And since 2010, he is Associate Professor of Atmospheric Sciences at the University of Alaska. He has lots of publications, over 60 peer-reviewed publications and a whole bunch of conference talks. So I'm really looking forward to it, his talk today, an integrated view at the high latitude, atmospheric boundary layer, and surface-atmosphere interactions. Okay.
Thank you so much. Happy to be here, and thank you so much for inviting me. And so I hope that we can get through this, and I can show you something that eventually, may be different from what you have been seeing, actually. So the first slide actually is my flyer, okay? So because all the faculties we have to pull out and see how we can get students on. And the first photo actually is temperature on the canopies, actually, where you can see ramps, low frequency turbulence on top of stochastic turbulence. Basically, this is one of the Boreal forests, and this is one of the scintillometers. And to illustrate the complexity of the environment where we are, you can see fog layers developing very locally on that Boreal forest. This is right on the back of the Geophysical Institute. See, those are some photos, me climbing a tower. I'm climate certified. Because in my group, actually, everybody has to be certified so that whenever we go to develop any field experiment, even if I'm not climbing the tower and I'm wearing the shotgun because it's bear country, actually. So the point is that you have to be able to climb the tower if something happens. So this is me in Chile, actually, doing outreach for NSF, actually, with the kids. And basically, this one here is one of the best expressions we can have, the turning of atmospheric sciences based on LiDAR profiling, okay? I think that everybody will agree here that atmospheric science is different after the LiDAR came on. Unless, when Charles will say that radars are really very important, but anyway. So so I do teaching. My teaching actually comes out in micrometeorology and boundary layer physics. That's my area. But also I do core classes in cloud physics, and as well in undergrad theory of flight, in which we are, since the university actually got into UAVs and UAS development. So the deans of engineering actually asked me to go into and develop the theory of flight classes, which is basically applied physics, but in a different environment, okay? So there we are doing actually UAVs for the community to start mixing up within the campus, okay? Because engineering is in one side of the campus and we are in the other side of the campus, and we have all this battle So anyway, this is the outline of my talk today, actually. And so we will be talking about technology and methodology, but then we will switch into some science application to then conclude in a summary that actually will get back into the abstract that I sent to you, which is basically the main research line that I've been working on. So basically, just to start, actually, LiDAR normally, as a backscatter LiDAR, normally works in the way that you have one polarization, and then normally you don't analyze the polarization in the receiver, but then there are polarimetric LiDAR that actually do analyze the polarization in the receiver. But the idea here is to see if we can go beyond, actually, and try to get more information on that polarimetric stuff. And then that's why I'm putting here the Mueller matrix, actually. So this is a 4x4 matrix that contains the entire scattering process, either in clouds or in aerosols, and this is the Stokes vector of the laser emission, and this is the Stokes vector on the laser in the receiver. So 1100 is the configuration for a normal backscatter LiDAR, 1100 is a non-polarizing LiDAR, 1-100 is for a polarizer, a polarimetric LiDAR. But the one that I'm going to show you is a little bit different, and I will show some examples just to go on with this. So for some particular environment, anisotropy in the scattering come into play. For example, if I have cirrus clouds embedded in a strong current, actually, I will have a very high depolarization fraction, like 0.5, 0.7. But actually, we don't know what if we are really sensing that, rather than an anomaly in the scattering because of the orientation of ice crystal. This is just to show you some ideas of when those polarimetric systems actually, polarimetric elements actually comes in. So how to turn the polarization in the laser emission? Actually, I'm using a photoelastic modulator. A photoelastic modulator is a system that has a piezoelectric device that actually, with a very quality control, 42 kilohertz plus minus 1 hertz, actually, you can produce a density, a refractive index variation that actually introduce in the laser emission a retardation level that actually turn the polarization of the laser, okay? So here is the device being tested in my labs, actually. So the laser, polarizer crystal to clean out the polarization, 6 dV, so very clean. So then comes the photoelastic modulator and then an analyzer to actually test the time in which you have to launch the laser to actually produce the desired polarization state, okay? So now, of course, the problem is that normally in a LiDAR, the laser is free running, not free running as a laser free running, but free running in the pulse repetition frequency, and then you catch up with the acquisition system. However, in this case, it doesn't work like that. Why? Because we need to synchronize with the photoelastic modulator. So here is the selection of the polarization that you want in the computer, and then we take one leading edge of the photoelastic modulator, and then we time with an electronic delay circuit, 100 milliseconds, to actually match up the sequences of the photoelastic modulator with the firing sequences of the laser. However, the key thing is to actually acquire the right delay so that you can make through the laser pulse through the photoelastic modulator at the time that the retardation level is the one to produce that polarization. And we can do that because 20 nanoseconds pulse width actually compared with 42 kilohertz is like being frozen, okay? So then the light goes through with one polarization state. Here is one detail on the design of the receiver, actually, because these lasers, this laser in particular, the one that I'm using, is a neodymium OPO, actually. And so it's basically, I will say, a non-technical word here, but the beam is a potato, okay? So then it opens up, it's 10 milliradian, so you have to correct. So I arrived to correct about 1 milliradian out. But the problem is that this device, actually, with the detectors that existed at one given point, indium gallium arsenide APD detectors actually has 200 micron diameter, and therefore there is a need to actually really be very careful about how you will collimate and focus into the optics. The design, I designed the telescope. The telescope is an F297, a spherical dark Kirkan, means that I don't have any window, because I don't want any polarization distortion there. So then also has, well, obviously gold coating, but then because we do operation up to about 60 velows actually, So then you need to hold the focal length of the telescope such a way that the beam that you are collecting from the atmosphere, it doesn't get out of the detector, and the detector is a 200 micron active area. So that's why we designed something that actually can be immune to temperatures. And the way to do that is to do a secondary. The secondary of the telescope is floating, and is attached to the primary with 4 invar rods actually, so that makes this, a non-varying in terms of temperature. So anyway, we did some other corrections with the detector as well. We are not using the Ingas detector as it is normally commercially. We are doing differently. So if anyone is interested, we can share that. So here is how we're going to install the receiver, because this is a section that still needs to be done. So we have done some testing already. So this will be done in a different way. The reason is because at the beginning, when I launch the laser pulse, it's 20 nanoseconds, okay? And then I produce the polarization that I need. But in the receiver, I have to analyze the signal at a fixed polarization for about 100 microseconds, okay? If I want profiles until 15 kilometers, if I want more, it has to be holded for more. So that in that case, you want to use some devices that are slow, okay, that can be fixed at one polarization. In this case, I'm using the liquid crystal variable retarders, actually, a combination of them to produce the linear and circular polarization states. And I think that there's a lot of things that we can do, because particularly in mixed phase clouds, in Arctic clouds, and in getting more information about aerosol cloud interaction is really very important for the community. Here's one example in which we're showing cirrostratus, alsostratus, and in the lower levels Asian dust, actually. This is in Fairbanks. And so we are pulling out in the old-fashioned radar, actually, the differential reflectivity, the sum and the difference between the two, and we are switching vertical and horizontal polarizations in the receiver without any detection on any polarization detection. And then by doing the calculation, we can come up with the linear depolarization coefficient at different levels, actually. Okay? So this is one application that actually demonstrated over time that we can actually produce polarization analysis without having a polarization receiver, okay? So this is another example, this is in the Pacific Southeast, actually, in Chile, actually, during the Focus Rex, actually. So there the LiDAR was initially intended to be pointed to monitor aerosols, actually, but then because the scintillometer that was intended at the beginning from Chile actually didn't work out, and then I have to move down to the shoreline, actually, basically near the ocean, the LiDAR. So here what I'm showing is just the ability of this to detect aerosols that were outflow marine boundary layer, actually. And at a given point here, there is no cloud. It's only moisture in the boundary layer, okay? And at a given point after that, these are the sequences of LiDAR profiles after this midnight, okay? I have to decouple this because the scale actually goes out. So here we see the aerosol layer outside the marine boundary layer. This is a typical marine or boundary layer profile. And then at one given point it's entrained and swell into the marine boundary layer, and then you can see the increases of 3 or 4 times actually backscatter inside the marine boundary layer, okay? So this is just one example. Now we're gonna switch to another project that I'm doing now, actually, halfway I'm doing. So this project is about an ice LiDAR, I call ice LiDAR, but the idea is to do polarization, linear polarization, standard, plus Raman spectroscopy. In this case, we are looking at the normal typical vibrational lines of nitrogen and water vapor, but also we are looking at water vapor clusters, okay? So 2 Raman bands actually that are located around the isosbestic point, actually. One with direct dependence on the temperature and the other with inverse dependence on the temperature, so that we can see the formation of ice and icing, and then obviously the interaction of aerosols with clouds, actually. So these are the lines that we have calculated. And at the beginning, this is going to be a project in 532, so a green laser. And that's it's not an optimal, I know, but we will see if we are successful, we will go on and do the 355, because actually 355 will be that we will be able to go through the troposphere, the entire, this will be 3 to 5 kilometers maximum. And ice is okay in Fairbanks, 3 kilometers, even in the ground actually, okay? So it's not a problem. So then, the idea is also to add the rotational lines actually of nitrogen close to the laser line so that we can also do temperature at the same time. So then we can have the entire thermodynamic in there, okay? Plus polarization, which actually will allow us to see aerosols and aerosol cloud interaction. This is the idea of how this will be set. So I know that I can go into a spectrometric configuration, but I prefer not to do that because the optical throughput is very low, actually. And in this case, what I'm going to be using is a combination of dichroic mirrors and razor edges, actually. And then by using angle tuning, actually, I will be able to locate the bands that I'm looking for. And also, this comes back to the 532, actually, because if I want to look at the Raman spectrum of the clusters, actually, in 532, I will have about 10 nanometer gap, actually. However, if I want to do this in 355, that's going to be about 5 nanometer gap, actually. And that skyrocket the optics, actually. You go into very expensive things, actually. Okay? So anyway, so this is the prototype here that we are setting up in the laboratory to do the calibration. And the first light will be in the AMS conference, actually, in January, I think is, Seattle. So now I'm going to switch into developing methodologies, and I took two examples, actually, on methodologies to illustrate where we are and what we are doing on this. So this is a paper that just came out in JTech, actually. It's about evaluating the spiking methodologies, actually, for turbulent sensing. And we are talking about sonic anemometers, okay? So then the spikes actually are one of the things that are really very important to get rid of in the signal. And actually, the spiking is a forerunner toolbox that actually goes into any eddy covariance process that can be in place, and is the only one that actually touches the data, modifies the data, okay? So you can later on do low pass, high pass, whatever, but this is going to be how it is. So we have different methodologies, okay? Statistical based methodologies like Vickers and Marr is the one that is being in use actually by most of the AD Pro, for example, one of the platforms actually, widely used by everybody. But I also, in spectroscopy, I developed some other technologies actually, because this is a common problem actually. It's a common problem also in climate series, how you get rid of unknown spikes, okay? And this is, so I have some interaction with Noah Princeton actually about this problem. So there was the paper that I like is Hostrup actually. This paper was developed during the time that he was here in NCAR actually. And it's a very interesting, we use his expression to actually generate a synthetic signal. So the problem here was to evaluate the methodologies and see what methodology would be best to actually be best, but also very performance, but also simple to implement to process massive data. And here we come to one paper, which is the Brock paper. So I imagine that everybody processing radio sounding data knows Fred Brock paper, actually. Wonderful paper, incredible. And so we took that, so in order to evaluate all these methodologies, we took a common framework, and that was to design a synthetic signal, a synthetic turbulent signal, which actually comes with no spike, so clear synthetic signal, and spike synthetic signal, and one with a spike. The idea of that is that once you have a time series, let's say 1 hour, 2 hours, of a synthetic signal where you know where the spikes are, then you can test the method, okay? So, because you know where those spikes are. So we use a histogram. So basically the idea is that we have the signal and then we filter the signal with one of those methodologies, and then we do the difference between the signal, the actual signal, and the filter signal to actually come up with a histogram of differences. And then the spikes will come out immediately, okay? So then you do this in a recursive manner so that then you walk from this one histogram to this one whenever it's totally clean. Here is the table to evaluate this, and so you can see that Vickers and Marr actually misses a lot of those, particularly because if the signal is non-stationary, and then you have to do a lot of arrangements with the window that you are using, because it's based basically in the mean, and our algorithms are based on the median. Okay? So this is one example of the Lindenberg Observatory, actually, in Germany. So we asked for this data, which is an airborne data, CO2 data. Okay? So next step, actually, is to develop or analyze which method will be proper for dropouts. Dropouts is really interesting because these are cases in which the signal goes out and continues there. And after a while, you don't know because the signal becomes autosimilar, and then it's very difficult to actually produce a detection of that actually you are within a dropout, okay? Same with gap fill data. Gap filling data, actually, I don't know what methodology are you guys using, but actually the one that I believe that I would like to implement is the one that actually emulates this. So that says, here is the signal, and here I have the gap fill, so I want to explore the statistics of the flow right before the signal so that I know a little bit of a history of that flow. And that comes out to non-standard statistics, like, for example, an empirical function. Okay, so right before the gap fill, I go on, or in previous replicated samples, I go on and build up the statistic function, actually, that belongs to that type of data, actually. Okay, we can argue and we can discuss about that, but I think that this is where I mean, I discussed this with Neon, actually. Anyway, so this is another methodology that we developed, as was said at the beginning. I do also laser scintillometry, and that requires basically, the idea is that you do measurements of laser intensity across a large area, okay? So in one side you have a laser emitter, on the other side you have a receiver, a refractive telescope, and then you are imaging the laser emitter in the telescope, and then you measure the intensity that goes through the field, and that intensity will be modified by the presence of turbulent fluxes, actually. So because delta T is produced by the turbulent fluxes produces delta refractive index that actually modify the amount of scintillation of the laser through the area. So now, using this measurement, these are direct measurements of average intensity and standard deviation of that, then you can build up and calculate the refractive index structure of turbulence, actually, or the turbulence of refractive index, okay? But, so Cn squared. And as everybody knows, Cn squared, or maybe so Cn squared is A Ct squared plus B Cq squared plus C TQ squared, okay? So it has a variation with the relative humidity and also with the temperature. But in the optical range, it's only dependent of ACT squared. In the microwave range, depends on all of that, okay? So now, based on that, we can transform Cn squared into Ct squared. And this is the only one measurement that we do that is area average, which is distributed. For the ones that we are engineers, we are, localized parameters and distributed parameters. We understand that. So distributed fluxes, okay? So these are just the effective height, actually, that is the actual topographic height multiplied by the function that obviously takes care of the system is sensitive mostly in the middle of the path, not close to the receiver or close to the emitter. So now the problem is that we need to, normally the problem was that you need to use the Monino-Bukov similarity hypothesis, because it's an hypothesis, not a theory. Okay, I just remarked that because I have to correct in all the reviews that I do that actually is a hypothesis. An hypothesis is not a theory. So now we do this, all this equation to actually come up with what the flux is by using the rho Cp, okay, normally, and then you start the friction velocity time the time scale, the turbulent time scale. But the normal way that this was done is by cycling, by proposing one value of the Bukov length, actually, and then cycling all these equations. But if you see, those equations are non-linear. And actually, by the order of this fundamental problem, actually, as you know, you might find solutions that are not possible, okay? And this was demonstrated by some other guys, actually. So now we put our heads into this, and then we put all these equations all together. Okay, we work it out so that we found an equation, an analytic equation that solved this problem. For a given Obukov number, actually, we can actually solve by recursion. Okay, this equation, we get the number, and then with this methodology, there is zero computational error, actually. So the errors will be associated with the signal-to-noise ratio of the signal you have and other parameters. This is in this publication in the boundary layer meteorology here. So then the next step was to actually say, look, I have the fluxes, but then now I need to know how those fluxes vary depending on for example, topographic height, okay? Because it's known that if you are if the laser beam is very close to the surface, then it will be the CN square will be very high, okay? And then CN square varies, very dramatically as it gets off of the ground. So anyway, that's why this methodology allows us a path, a systematic path to evaluate all the sensitivities from the flux to say what is the error compared with for example, with the topographic beam, the height of the topographic beam. This is another publication we got into atmospheric measurement techniques, actually, from Copernicus. So anyway, what I'm doing now, I'm working out the sensitivity functions compared with temperature variations and friction velocity, because we have seen in basins actually that, basin that we have there, but everywhere you will see the same thing actually. Variations of the frictional, the U star actually as the direction of flow change, and this is really very important to consider actually, and in terms of how these affect the calculation of fluxes. So now, I will turn into applications of, science applications, so to say. So the first one is in the summer. There's going to be something related to smoke and fires. Actually, this is after this was a period in which we have a lot of fires in Alaska, actually. And so you can see, this is the first light of that LiDAR, actually, 1.5 microns, just pointing vertically, and this is 1 day 29, and this is the 30th, actually. So you see two boundary layer developments that are completely different, and also you see, and obviously I was testing the instrument, that's why the signal-to-noise ratio is really very, very bad, actually. But it was enough to actually say that actually we have a plume at the beginning that is decoupled from the boundary layer that actually after a while actually gets subsiding actually. But at the same time we have another plume that is on the outflow boundary layer that actually get entrained during the diurnal cycle, okay? This is a plume that hangs over the boundary layer that never get entrained, for example. So 2 days with a completely different picture in the surface. This is the PM 2.5. Actually, in the transition from the night to this day, actually, this is the transition, okay? We have a jump on the PM 2.5, and also we have 2 other spikes on the PM 2.5 due to that entrainment process. This is something that I've been working since my thesis, actually, and this is the downward mixing process, okay? So normally, so air quality managers will say, well, look, overnight situation will be very complex because the boundary layer will collapse, concentration will increase near the ground, but next day, the situation will clarify because the boundary layer will increase the volume and concentration will obviously reduce. And we know that, but here's what happened. There is a counteracting effect, actually, in the boundary layer cycle because of the presence of those plumes, actually will, that instead of cleaning, and this is what is seen here in these photos, actually. I'm pointing the same place, actually. This is before noon, and this is in the afternoon. And you see that you expect in the afternoon to improve, but actually it's worse, okay? So downward mixing in the boundary layer, I have several papers on that. Because this is also related to the nocturnal to diurnal transition, actually. And this is something that has been looked here, for example, New England Air Quality Project from NOAA, actually, because it's also something that comes in when you have ocean flows, air masses that come into land, actually, that get entrained into the local boundary layer, okay? anyway, that's one result actually out there. So this is another project actually called Wyblex, Winter Boundary Layer Experiment. And this is a project actually that I was interested in doing, where we could have different profilers here, but also the large aperture scintillometer. This is the university, the West Ridge actually, one of the sites of where we do normally science. And so engineering is in the other side. And then this is the farm actually. And so here we have met towers and Doppler acoustic sounders and LAS and eddy covariance. So basically the situation is like this. During the winter, you don't have shortwave radiation. So if you go into the energy balance, you have to cross the shortwave components. And then you have a surface that is basically dominated by long wave radiation, okay? So therefore, the problem is that this boundary layer can be fragile, is easily modified by flows. Okay, and therefore, so here's what happened. This is what we call the Fairbanks Bowl, actually, because it's the Tanana Valley where Fairbanks is here. But also behind the mountains, actually, we have another valley, actually, which is about 10 kilometers long, actually. And there, the temperature goes 15 to 20 Fahrenheit lower than here, okay? So then under these conditions, and under, for example, very low pressure gradient forces, actually, you will enable those small-scale flows to come in, actually. Okay? So and so the way that this comes in is in two ways, actually, basically. So there is one way in which is intermittent, more likely a drainage flow, while there are other ways in which it comes with a little bit of mesoscale forcing, channeling through, I will say, and then it's present practically all the time. This is the vertical velocity in the anemometer that shows that you have bursts of turbulence coming in, and then it goes quiet, and then goes back again and things. So at 30 belows or 40 belows, it's very difficult to stay there, I can tell you, because this wind chill is so incredible, actually. So here is one of those episodes in which we are seeing the CT square coming out of the acoustic sounder, actually. So that delineates very well the limits of the flow. So 100, 150 meters, no more than that. And then here is the correlation between the fluxes by the eddy covariance and the large aperture scintillometer. And you may expect, that under snow covers, you will have basically the same thing reading by the two instruments. However, because you have a flow that is varying with different dynamic scales, actually, the anemometer, I'm not sure that the anemometer is picking up all those scales, while I'm sure that the large aperture scintillometer is picking up in the entire active area, actually. And this is the signature of the negative fluxes, obviously, from the aperture LAS system, actually, the scintillometer. So applications of these are great, actually. For example, there are Yukon Flats, actually. That's a place on north of Fairbanks, actually, off of the Brooks Range, actually, that has the same type of features, actually. And permafrost there is one of those. And you may say, look, I know by the theory that snow covers actually is an isolation. No. Actually, if you have storms, this is something that I show in my classes, actually. If you have storms and you are sensing underground temperatures, the storms flying over the Arctic will dump snow, and the snow is warmer than the surface, actually. And then it will, over time, will warm even the subsurface, actually. Very important for permafrost regimes, actually. One thing that we are looking at studying, I mean, the paper was published in Meteorology and, I'm afraid, Physics in Springer. So, but we are looking at this, and perhaps, it would be interesting to develop some collaboration. But the idea is that I see shear, okay, in the CT square in upper levels. And I wonder if part of that shear actually is reflected and feed back into the fluxes on the surface, okay? Because when you have shear, you have your eddy actually, which is like this, okay, or maybe not, maybe like this, and then shears, okay? Breaks. When it breaks, this part may be contributing to the surface fluxes, okay? So we have data, a lot of data, and we will be looking for collaborating with modelers into that. This is an IOP, and I'm sure that this laboratory is plenty who have knowledge of IOPs, intensive observing periods, actually. And so anyway, this is just, I mean, well, the resolution is a little not really very good, but anyway. So there was a student, actually, I was helping, and then we did collocated solder and radio sounding measurements. And this is, we were testing also the MK2, actually, GPS sounding, actually, because all the NWS system actually was turning into that, actually. And so, and it was a great opportunity, actually, to look at breakup and formation of a surface-based inversion. So I guess everybody maybe know actually what a surface-based inversion is, but I'm just going to review a little bit. So normally this will be the temperature profile, 3 p.m. Okay, and as the sun goes down, the heat capacity of the surface is much smaller than the air, and therefore this will cool. Okay, faster than the air, and therefore will create the first inversion with base at the surface, surface-based inversion. Okay. So now here with this, so you can see that having high resolution profiles actually allows you to track all the structures that are within very close to the ground, okay? After that, evaluating this measurement, I look at the isothermal layers, for example, generating that, inducing mixing, you know, as a result of mixing in the stable boundary layers. So anyway, so very calm situation, okay? 3 meters per second, actually. And so anyway, so what we found here was that at the formation of the SBI, there are two periods actually. One very fast cooling at the surface, okay, with a shallow SBI, and then after a certain point, minus 20 C, minus 25 C, depending on the vapor pressure actually, obviously the radiative cooling still is there, and it's profound actually. And then after that, there's a second phase actually in which the SBI grows, searching for a higher level of equilibrium, momentum, and radiative equilibrium. Okay, so this is one of the key results actually from that experiment. Okay, to find that we have two cooling phases actually. Then obviously we verify what we knew actually, that short-lived pulses actually produce mixing and then erase the structures that actually eventually come back in. So although this might not be, this was published in Polar Science actually, this might not be, I mean, it's relevant for air quality actually, because when this surface-based inversion builds up at 5 p.m., then you have an air pollution episode for 2 or 3 hours actually. But it's also important because the surface-based inversions are important to slow down the radiative cooling in the sea ice actually. Okay, so now I'm going to show something else actually, because this is related with what comes in here. So later on, and exploring some of the acoustic sounder measurements, we found some echoes higher than in the surface-based inversion. And this turned out to be what everybody knows as synoptic inversions, okay? And so that's why we came out to analyze this, and also because I've been analyzing some of the papers in which the surface-based inversion turns out to be around 300 meters, 350, and actually when we did the calculations and processing specific data, we found 150, 170. But the problem was that normally, as well, maybe you guys know, but the soundings actually record not that many points close to the ground, okay? And if you're trying to, for example, find the inversion through a fitting algorithm, then there's going to be more point here than here, and therefore the weighting function will be much better here than here, and therefore your inversion, you know, will be located about here, rather than actually where it is. So that's why I decided to actually take a look, a mathematical look at this problem and say, well, look, what we want to do is we will create a mathematical algorithm that search for slopes with, so layers that we can clearly identify. And that's what we did here, okay? So we approximate this with a mathematical algorithm to actually look into the different layers within certain error, okay? And we can come up with all the layers that are meaningful or that are important. So now the application of this methodology, the sounding get transformed in a data structure, and after that you can decide what to call the SBI, if it is the SBI or if it is an EI. EI is an elevated inversion. methodology is published in atmospheric measurement techniques, actually. So now with that methodology, we process about 10 years of data, or radio sounding data in Fairbanks, actually, to come up with the statistics of what the time series were about SVIs and EI1, EI2, elevated inversion 1 and 2. So here are, these are definitively non-normal statistics, okay? So, and that's why we build up the statistical estimator based on empirical probability density function. That's the one that I believe, okay? And so you can see for statistic for the SVIs, statistic for the first elevated inversion about 1,000, statistic for the second about 1,500, and then spreading out, okay? So one of the things that was interesting, because now when you blindly process data, then you don't know if that inversion was, well, we say it's a synoptic inversion, but what is the mechanism? And then we went out and we classified that based on the dew point temperature gradient across the elevated inversion layer. So if the dew point temperature increases across the elevated inversion layer, then we are in a moist inversion, while if it decreases, we are in a dry type of inversion. And that comes to two sources, cyclonic warm advection or anticyclone elevated inversion. Anticyclone, as you know, it generates and then over time actually will wobble over the area actually to accommodate itself until produces the adiabatic compression, which actually will warm up the upper levels above the boundary layer. So one of the results that comes out that is very nice from the statistics is that actually the elevated inversions that are produced by warm air advections actually comes statistically very narrow, actually. They come close basically at the same level or similar levels. While the ones produced by anticyclone, because of this process of adiabatic compression, actually, it can be heated by the radio sounding at different levels, and therefore the statistics actually is more broader, actually. So here is another slide that actually shows how these inversions actually then becomes key players in the surface-based inversion to actually come up to a point in which this is the surface-based inversion form here, but the elevated inversion over time, these are the 0 Zulu and 12 Zulu, okay, soundings all the way, until you basically erase the entire surface-based inversion, okay? So this, everybody is talking about this, so how the warming will come, actually, and I believe it's gonna come through the extraordinary forces of the synoptic meteorology. Extraordinary and forgotten. So now let's turn ourselves into heterogeneous canopies. And here is one analysis that we have done actually. Basically, this is a traditional type of analysis in a micrometeorological tower with multi-level actually. So in the Boreal forest, the difference with all the other forests is that this is in discontinuous permafrost with organic layers, okay, and with very funny trees actually, which are the coniferous black spruces actually. And so we have a micrometeorological tower that has 3 levels, 3 meters, 12 meters, and 24 meters. Sonic anemometers, and then also have so the area, the height, the mean height of that area on the trees actually is 4.5 meters actually. So one of the anemometers is sub-canopy, and the other is above canopy, and the other is looking at larger areas. So anyway, the idea is that as the flow enters a zone, a region of highly heterogeneous surfaces, then it will develop vorticity, okay? So, and then it will displace actually the zero. So it will display. It will be such a. It will be this inflection point. It will develop an inflection point on top of the canopy actually, and then so the turbulence that we analyze normally has these conditions. Have the mean flow, the stochastic part of the turbulence, and then the low frequency turbulence. And that low frequency turbulence comes because of these vortices actually at having, having these changes in heterogeneity, actually, the vortices actually can, it's like an spaghetti, actually, okay? So spaghetti actually can accelerate or decelerate, okay? And by doing that, the spaghetti will produce positive static pressure or negative static pressures, which are motivating the sweeps and ejection, and these are known in hydrokinetic as well. So, but in the literature, actually, there are a number of elements and discussions, and I think that there are some experts here in this element, that actually about how these vortices are generated. And there's one that says that to maintain momentum balance, actually has to be two vertical elements actually that will be detached actually, and that's explained some of the cases in which you see this detaching, but a little bit higher in the canopy and lower the other end. So anyway, we processed the time series because we were looking at what the fluxes and what the contribution of those fluxes were in terms of stochastic and low frequency turbulence. So we measure the spectrum is about 1/300 seconds. So it's before, so in the subinertial range actually. And then, so we use wavelets actually to process that and then identify within the half-hour period, which is normally what we process in micrometeorology, those events, and they slice out which ones were coherent structures, which one were stochastic motion. However, there are a number of elements here that were not exactly like the ones published before. First one is synchronicity. So it was illustrated in one of the first papers from UC Davis, actually, that the ramp occurs at the canopy and then simultaneously occur in the subcanopy. And actually having exactly the same, all the two sonic anemometers, the 12 and the 3 meters, located in the same data logger, actually, so no delays, we show that the synchronicity happens whenever you open a window, or 10, 20 seconds, and then you can start talking about synchronicity. Okay? So that's the first thing. The second thing is that actually, we got the same, basically the same duration ratio, 85 seconds per ramp structure. The amount of contribution to the fluxes is about 50% if you consider the entire turbulence field, okay? So low frequency plus stochastic, okay? So there are some discussions about that, particularly the Germans actually, Fochen is one of those that actually decouples the stochastic turbulence within the low frequency turbulence, okay? But this is something that I'm not going to enter into that discussion. But so anyway, so the point is that sometimes some of these time series, as I show in the first one actually slide, verify a behavior that can be also associated with waves, with gravity waves, subcanopy waves, for example, okay? So then there is a need in the time series analysis to decouple whether you are under a turbulent process or whether you are in a wave-like process. And here comes the next problem, because the problem is that in normal canopies, I believe, in mid-latitudes, you have a thermodynamic inside the canopy that actually is well-behaved, well to say. But here, we were undecided what to do if we take delta T, because the way to discriminate is to pull out the Brun-Weishaler frequency and say whether you are on the wave or not. So now if you put 24 over 12, 24 over 3, or 7 over 3, we were having different things, different periods in which we will consider delta T to ingest into Brun-Weishaler. That's why we went into this new approach, which is an approach coming from electromagnetics, actually, from electromagnetic waves, actually, to pull out the Stokes numbers of the flow. And basically, a flow that is under a wave-like motion will have to have some sort of correlation between U and V. And that's what you pull out if you do the Fourier transform of the U and V components, actually. But has to be done with a window. And this is the window, because you want to evaluate if at the moment that you have the coherent structure, you are under a wave or not. That's the point. And then you have to do this band, with band limited actually, band limited to this, and then to pull out these numbers, and then with the linear polarization, you can actually see and discriminate events that are turbulence and events. Actually the ones that are with wave actually. Okay? So that was published in the JGR atmospheres, and this is another study that we have done because I was collaborating with remote sensing researchers. And then obviously one of the key questions is, MODIS, for example, has 6 readings per day in the high latitudes, and then the point is, can we do fluxes in large scale if we read radiometric signatures? Well, the radiometric signature comes with 1 kilometer footprint. And then the question is the eddy covariance tower in a canopy able to pull a flux equivalent to 1 kilometer? And here's the thing. This is one tower, okay? DC is dense canopy, in a dense canopy, and SC is sparse canopy. So the distance, straight line, is 600 meters between the 2 towers in the same environment. This is in the campus, okay? So here what we found was that actually processing all the fluxes between DC and SC, I went out to look for different things, to be honest. I went out to look at a sparse canopy, canopies that are about 1 meter height actually, or about that, but where the atmospheric flow is more in contact with the surface and therefore with the thawing of permafrost actually. I was looking at this holy grail actually to get the actual permafrost thawing signature, with the latent heat. But when we process the latent heat here and here, it turns out to be about the same. All right. So then, before collapsing, we say, look, we have something else here. And we computed the fluxes, and then you have, beyond all the statistical differences and all the instrumental differences, we found systematically over selected periods in which you have clear skies, very good developments of the boundary layer, you have 50 watt per square meter difference between these 2 sites, okay? So then that sets a point that actually, what is the radiometric signature that I will use to produce the large-scale fluxes? Because all of these would be within the same pixel for MODIS, okay? So now, we found another thing, actually. And this is really very interesting. The turning to a stable to unstable in the boundary layer is what we call transitions, okay? So well known the unstable, less known the stable, and not really known the transitions, okay? So now, but here's the thing. When we process the temperature profiles across, and this is a composite of all the days, actually, we found that obviously systematically one place is colder than the other place. However, we found also that the transition to a stable to unstable, or unstable to a stable, actually takes between 2 and 3 hours to homogenize, okay? So to say this forest that I'm taking from the satellite is under a positive flux or negative flux takes about between 2 and 3 hours to get really homogeneous, okay? That speaks about some other elements that we found actually, like thermal bubbles that are impossible to capture by the eddy covariance, but you can have this through the scintillometer because it's a area average. Anyway, as well, there's a paper in JGR that you can take a look. So now let's switch over developing multiscale fluxes, which is one of the things that is really interesting for reaching out other communities, actually. So here is north of a brook range, okay? North of a brook range. Here is Barrow here, Prudhoe Bay over here. This is a basin called Park Basin, okay? This is the one that everybody sees on the movies, that there is water on in the Tundra, okay? So here. But we are exploring this basin, the Imnaviet Basin, and this is a basin that has about 20 or more years of hydrological research, okay? So this is the scintillometer, okay, looking at the brook range. And so now here is a topographic map of that area, and here is more in details, okay? And this is with the synthetic aperture radar, and you can see some stripes here. I mean, the details are really, I will give the PowerPoint to you guys. But these are water tracks, actually, that has been detected using synthetic ABL radar. So this is 2 kilometers, about 2 kilometers, a little bit more, and this is about 1 kilometer, a little bit less actually. And you have topographically a basin that this is east-west, and it's going down toward the west, and it's gauged here so that the hydrologists actually can do water mass balance, okay? So here are, so we have one, there's one AON, I mean AON, everybody is Arctic Observing Network, AON, there is one eddy covariance tower there, and I put another one in the north, so this is in the south, the AON is in the south, I put in the north actually, and in between the two I put the scintillometer, but on the ridge area, so in the higher elevation, okay? So these are the time series in the Naviat Basin, where the red dots is our eddy covariance tower, and then the blue is the eddy covariance tower from AONs. But you can see systematically the large aperture scintillometer actually reaches much higher values on the sensible heat flux. And we're talking about sensible heat flux only, okay? And so basically, my understanding of this is that as the boundary layer develops and takes over more heterogeneity, okay, so then the flux at the larger scale actually is a little bit different. In some experiment that has been done in Germany as well, they have put one eddy covariance tower close to a region in which the roughness is very high, and the scintillometer across that area. But the scintillometer, by picking averages, you know, it will pick the region of high flux, but also the lower flux. And that's why Beirich publications actually is saying that there was cases in which the eddy covariance actually picks us more flux than the large aperture scintillometer. Here is our work, but within the context of satellite remote sensing. Okay, so satellite remote sensing actually gets a handle of this. Okay, they know how to measure short wave, long wave. So they do net radiation, but high level. Okay, high in the, not within the canopies. Okay, so then our work actually is first that level to screen out what is RNet canopy, RNet soil, and from that the RNet that goes into the soil. I mean in the surface. Okay. And then from there, we have to work out this, which one is the portion that goes into the ground, and which one is going to be expanded into sensible and latent heat. And then we work back again, with Bowen ratio. I know that everybody hates that, but that's the only one way that in remote sensing you can do. Anyway, this is a very bulk model of the canopy, actually. This is the two-source energy balance model. This is not me. It's just these guys from USDA, actually, in Bettsville. And so they have a way to actually work out the entire thing. But here is the result of the model applied with the correction of the scintillometer. Because here's the thing. You do your calibration of the model with the eddy covariance tower, but then you ingest the satellite data, and then you come up with fluxes that are not at the level of the eddy covariance, are at the level of the footprints of the satellite. Okay? So then you have the problem that you need to correct. You need to give up the closure, actually, that give you the laser scintillometer. So here are observed flux and then model flux. And the radiative fluxes are kind of good. So we have some residuals in the latent heat, actually, okay, that build up over here. But the most prominent and the most difficult, actually, is G, the heat on the ground, actually. And because there is a lot of diversity, anyway. This is the result, actually, the map of evapotranspiration. Here is the brightness temperature, actually. You can see that this region is colder because it accumulates water, okay? And this is more warmer, actually. So, and that is reflected, in high values of latent heat. So people are interested in this. NASA has a product that is processed by Montana University, so the Thermodynamics group, actually. And so in this latitude is really very important, actually. Let me walk through the last application. I'm sorry, I think that I'm out of the time, actually. Okay? Can I continue a little bit? Or? Okay. anyway, so I mean, this is the last thing actually. So basically, taking measurements of eddy covariance and large aperture scintillometer, we come up with an idea in which you can actually. So what people are looking is to know what is the upscaling coefficient would be. Okay. So what the upscaling will be. So what my measurement at the local level would be at kilometer level, okay? So this is what also is called regionalization of the fluxes, okay? So now here is an experiment in which we process heat from eddy covariance and loss, and also we put this as a function of the overcurve length, and you can see that there is a empirical parametrization. This, I have to submit this paper actually, but this is a preliminary empirical parametrization. The idea is to put the upscaling for a given environment into parameters that we can model, or the modelers can model, okay? Okay? So that's one idea. So as a summary, I'm just going to finish with that. This is the point. Surface atmosphere interaction are central in understanding weather and climate. The problem is that all the models are working on a footprint that is completely different from the footprints of the measurements that we have. So anyway, quantifying this relationship in addition, because the problem of the fluxes is not a problem of a surface. It's a convolution between the surface and the flow, okay? And that entails the dynamic of the flow. And that's why what I'm pushing forward is to actually combine those surface measurements with boundary layer measurements. This could be at the beginning just dynamic of the boundary layer, just the height of the boundary layer, but also could be tracers like vapor, water vapor, like CO2 as well. Okay, so there is a report that I submitted to NEON CEO actually. Last year I was visiting scientists in NEON to actually work out the connection between biotic ecosystems and boundary layer dynamics actually, and the atmospheric systems actually. And I think that is the connection, and I think that we can provide that. So there are many organizations that you can see that will be looking into that. So this is a little bit more about that. That is a collage of, I like French words actually, of the entire system of measurements we do. And this is scales, and then spatial scales and temporal scales, in which we have different instruments, okay? Eddy covariance, large aperture scintillometer, LiDARs, and different satellite platforms, and different modeling capabilities. And I think that this is something that it would be interesting to turn it around, actually. So anyway, so what is upcoming? And with this, I'm done, actually. So I will be working on developing a workshop that we discussed with NEON, actually, to put together these communities and start building up that connection so that we can eventually study the need and create that need. And then I will be working with a new setting that we're having actually with a micropulse LiDAR that will be 24/7 working near my micrometeorological sites. Then new technology, I'm looking at developing dial combined with Doppler LiDARs actually, to actually look at differential absorption LiDARs, so to pull concentration, but also to pull vertical velocities, so that we will be able to do volumetric fluxes, because volumetric fluxes is what will be talking the surface with the rest of the atmosphere. And then new field experiments. I'm looking at this, for example. I'm working with Penn State, actually, to develop a biogenic volatile organic carbon, actually, study. I was about to join the last spring experiment in Ann Arbor, actually. Prophet is the experiment, funded by NSF. But actually, I'm interested in looking at the turbulence influence on the formation of nanoparticles, actually. And so Penn State actually is very interested on working on that as well. And then I'm looking at, in the international sphere, actually, I'm looking at iodine aerosol. Maybe you haven't heard about that, but actually those are iodine products, actually are halogens, actually, that are produced when the algae actually are exposed to the solar radiation. And then iodine in the atmosphere goes a very fast oxidation chain, actually transforms in IO, I2O2, I2O3, I2O5, actually, and then becomes nanoparticles, actually. And the process of that is still not known, fully known. And also, there has been some research by the British, actually, and they have done ice cores in a transect inland in Antarctica, actually, where they have found different iodine aerosol concentrations, actually. And the question is, in the future, if the Antarctic ice sheet actually goes down, actually, how much of that iodine will be free, actually. And iodine, as you know, has a very powerful oxidative capacity, actually, and this is very important for the atmosphere. So anyway, and then we're working out with the NSF Oden, actually. There is a NSF Swedish collaboration to actually do operation in the icebreaker in the Oden. So we are looking at low-level cloudiness formed after fluxes in polynyas. So I have collaborators in the MISU, in the Meteorological Institute of Stockholm University, to work on that. And thank you very much for standing there. Thank you.
Okay, thank you very much. Since we ran a fair bit over, are there any burning questions? There's one burning question.
Go ahead.
You mentioned about differential reflectivity in LiDAR.
Yeah.
There are a lot of measurements done in radar the similar way. I was wondering whether, have you compared any of those between those?
What was it?
Radar measurements that do
I
routinely
haven't done radar memeasurements. But let me tell you this. Most of the physics that is known, and a great part of the physics that is known in laser physics was taken from microwaves. So yes, there is a lot, and I did that expressly, actually, to acknowledge that even though we're doing LiDAR, we are taking from radars technologies, actually. Yeah. So, but I'm not doing radar. Okay. But since you have asked that question, actually, radars normally use the Jones matrix for scattering as a 2x2 matrix. And the reason is because they can maintain the phase between the electromagnetic pulse that goes out and the one that comes in. We cannot do that. We could, but the laser will have to go through an interferometer, actually. Okay? So that's why we have to go into the 4x4 Mueller matrix, actually. Anyway.
Thank you.
Yeah.
Okay, let's thank Javier one last time.
Okay, thank you.